And what we've got today is about a huge amount of material. Obviously, I want to do the whole of today's session in 45 minutes. So we just 45 minutes is what we want to do today. And because if I talk longer than that, I'll bore you guys and ladies. And there's about 140 slides. So obviously, I won't cover every slide. I will cover the key ones, but you will get copies of all the slides. So don't fear, everything will be provided to you. You will get the whole lot. And in fact, it forms part of a larger 3-month course. So I've just taken the key bits. Now, also, I just want to tell you now that you won't become an electrical engineer after 45 minutes, although I'm sure there are many electrical engineers amongst you, but you will become a little bit more knowledgeable. And if you go through the slides and the additional learning materials we give you, you will become very knowledgeable. So don't fear that this is a waste of time. So I'm going to cover the key elements. Fundamentals, and I'm sure there are lots of engineers here, design rules, and commissioning of electrical systems. Now, I just want to also again mention we are covering the IEEE standards, which is the American standards, the IEC, and also I'll be specifically mentioning Australian standards as well. So there is a mixture of standards, so please don't say, Steve, it's wrong. This is the right standard. You know, you've said 1 ohm, it's actually 25 ohms for earthing resistance. I am trying to globalize the course because you people out there are all from all over the world. So I want to try and be as general as possible. So please forgive me for being a little bit perhaps generalized. It's not always a good idea, but I will cover the different standards. And as I said, I want to do it in 45 minutes, but there's plenty of materials here to go well beyond that. And after each section, I've got a little quiz. And in the quiz, I want you to be able to answer in the chat box. So please don't talk, but you can say, hello. Let me just say chat. You can all see the chat box. Please answer the quiz here. Okay. And if you disagree with anything, please put it in the quiz and I'm all ears and I will reproduce it. So what we're going to be doing today is first of all, generation, transmission, distribution. I just want to talk about what that is. Transformers, those curly devices which have very low losses. Earthing and grounding, which is a topic after my own heart. In fact, we just run a conference in Birmingham in England on that topic. Power quality, and then protection. So those are the main groupings today. And as I said, we will be going through lots of material, but I will just go through the key things. Now, the first question you should ask is, why bother about these topics? And I've headed all the topics here. Generation, transmission, transformers, earthing, grounding. Why bother? Well, there's a reason here. Obviously, power systems are critical. Your career opportunities are related to power generation, particularly in the solar and wind and renewables. Energy efficiency is really, really important. If you look at transformers, they are critical in power transmission. Energy efficiency, renewable energy, they're becoming important as well. Earthing and grounding, why is that important? Well, you've got things like safety, very important. One of the most important things in life is making sure you look after your fellow man and woman in terms of safety. Absolutely critical. And system reliability, equipment protection, and obviously compliance regulations and standards. And the other thing which is earthing and grounding is becoming important is renewable energy, because it's a completely new bunch of generation issues. Power quality has been around a long time. And why is that important? Well, again, energy efficiency. You'll find that renewable energy is causing some dynamic issues with power quality. And then power system protection wise, it's important. Well, protection of your equipment so you don't blow it up, obviously. Safety so you don't get killed or hurt. And again, renewable energy is becoming an issue as well. So hopefully these are all reasons for you listening in for the next 40 minutes. So first of all, power generation, transmission, and distribution. This is the first topic. And I've got it here. Boom. And by the way, we had about 1,700 people registered today. Unfortunately, we can only take about 400. So the people that can't get in will be getting a copy of the slides and obviously the recordings as you will. So don't fret. We've got about 300 here now. So welcome to the team. So obviously energy conversion is transferring from one energy form to another. That's important. And obviously one of the big focuses today is solar and wind. And obviously nuclear is another really interesting one. Now, at the risk of being shouted down by every dog in town, everyone in town, please bear in mind nuclear should not be discounted. Please think intelligently about nuclear power. It's not a stupid, dangerous idea as many people think. In Finland, the Green Party is even supporting nuclear power. So, you know, there are potential issues there where it's useful. Unfortunately, and that will be one of the quiz questions, is fossil fuels is very much a key builder and it is poisoning our lives. But again, there are some issues there. So electrical engineering is what it's all about, and the most important sources of power plants are coal and hydro and obviously nuclear. As I said, nuclear can be a little bit irritating. So there are a few facts here just for you to think about and to reflect on. If I can ask you to reflect on them, Mr. Shahid Hussain Rizvi, welcome to the team. Some of the global facts is 38.7 terawatt hours. How much is a terawatt? Please put in the box. Please tell me, how much is a terawatt? 10 to the power of 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Yes. Thank you, Mr. Raj. Mr. Raj, thank you very much. Absolutely. 10 to the 12. So 10 to the 12 is what it's all about. That's a huge amount of power, and it also is equivalent to 3.9 trillion barrels of oil. Can you imagine the pollution with all that oil? Not that oil's bad. We do need energy. We do need energy. I'm not saying it's bad. We do need energy, but it does create a huge problem for emissions. So it is worth replacing with something. Electrical losses are 6% of that is wasted. 6% is huge. Get your calculators out. 0.06 times 38,700 times 10 to the 12. That is a huge amount of energy wasted. And so that's a big issue for you as a designer. The largest hydroelectric power plant in the world is Three Gorges Dam in China, 22.5 gigawatts. Good gracious me, 22.5. It is horrific how big that is. And it's hydro as well, so it's clean. Now, if you multiply 22,500 megawatts times 10 to the 6 times 365 days in a year times 24, you won't get 100 kilowatts, you get 190. So this power plant isn't running all the time 100%. So those of you, I just want to ask you to always check. And obviously the other big thing is renewables. 72% of new capacity is renewable. So this is the big baby on the block, the big one that's going to blow us away. Solar and wind, that's growing fast. So that's always good to see. There's one problem with, thanks Rahul, thank you very much. One issue with solar and wind, obviously, and I'm sure someone will be complaining shortly, it's not a base load. In other words, it's not like a coal station going, it actually goes up and down depending on whether there's wind or light or sun. Dear sun, please shine on my panel today. So turbines are a critical part. and that extracts energy from the fluid flow. So fluid flow could be water or gas, or indeed steam. So you could have any of those. So it has blades. So that's the critical driver for our energy creation. And then you have a electrical generator, which you'll see here. These are generators. And this is, there's a little diagram here, which I'll show you. Here's a diagram for a generator. So this is obviously one of the critical builders. We've got water flow coming through. You've got a shaft going up, and we've got water flow coming through. You've got a shaft going up, and of course you've got a stator and a rotor. These are the two terms you often hear used in a generator or indeed a motor, and that generates electrical energy because it's rotating around and round. And it could also be water, gas, steam, etc. So this is the critical driver for creating of energy. And here's a coal-fired power plant. Unfortunately, this is very bad because obviously lots of pollution coming out of here. So this is bad news. So that's why we want to try and move from this to something a bit more sensible. So you've got, again, you've got your steam coming through here. So you've got a boiler, boom, steam and turbine, and then of course transmission lines. And this is where you get transmission, and then eventually you get distribution lines as well. Here's a turbine power plant. Can I ask anyone out there, what is the advantage of a gas turbine? What's the advantage of a gas turbine? So here's your gas turbine, combustion chamber, and of course you've got exhaust, and you've got, again, energy generated. Hello, better efficiency? Yeah. 50% of emissions of coal, yep. What's the other big advantage? Could be cheap if you've got cheap gas, yep. If you've got expensive gas, can be very expensive. The other thing is, yeah, it's dependable. The problem is with gas turbines is it can be very expensive to maintain, but they are very quick. Boom! You've got no energy, you push the button and you've got energy. Boom! Whereas with a coal power station, it's a long, drawn-out process. I need to warm up the water, get steam, get that steam through the turbine, so it's a huge process. Quick start. Thank you very much, Moses. Quick start. Absolutely right. Thank you. So thanks very much, everyone, for being so interactive. You out there are teaching me. Thank you very much. Okay, so hydroelectric power plant, two types, pump storage, and obviously the usual traditional hydroelectric. So in Australia, in Tasmania, so here's Australia, there's Tasmania, and there we've got lots of hydroelectric plants. What's the problem from the greenies' point of view? What's the problem with a hydroelectric plant? Can anyone tell me? I mean, hydroelectric plants to me are a no-brainer. It's clean energy. It's from the thing. Why do greenies not like? Yeah, flooding. You destroy whole towns. You destroy beautiful wildernesses. So people obviously aren't always so enthusiastic about them. Land use, absolutely. And you do get, takes lots of land. Fish migration. Absolutely, you destroy all the traditional things. And what is better than the natural world? Please, I ask you, what is better than the natural world? Walking amongst the trees, the forests, the little rivers running through. It is beautiful. We don't want to destroy that. But anyway, it's population displacement. Thank you so much, everyone. Less water, no energy. Yes, absolutely. And Ronil's hit a very good point. New Zealand had a huge problem a few years ago. They depend on a lot of hydroelectric schemes, and suddenly drought, no more power, mate. Sorry, no power. What the hell? Gee, that's incredible. So, you know, we've got to be wary that everything we have is got an issue. There's no free lunch in life. And then obviously pump storage plants are quite useful because in South Africa, for example, pump storage plants are quite useful. You pump the water up, and then it's like a big battery. So it's quite a good idea. And you can then, when when electricity is cheap, you can pump it up, the water up into the top, and then when it's expensive or you desperately need it or peak usage, you can then let it run. So it's quite useful. And Pete says it's a balance between the natural world and unnatural humans living in it. Thanks, Pete. Yeah, Pete, you've got it's a very tough view on life. But yeah, I suppose having no humans is probably a good thing for the environment, but let's not go down that way. Effect on aquatic life is also very damaging for hydroelectric schemes. Thank you very much, guys and ladies. So the nuclear power plant is another interesting one. And I just want to say, look, the minute that I open my mouth and say nuclear power is good, I will get shouted down. Please, Steve, shut up. No, bad news. But please, I want to beg you, look at it intelligently. Nuclear power can actually offer some opportunities. Obviously, you don't want a Chernobyl situation where the whole place is leaking radioactivity. That is an absolute catastrophe. But the good thing about nuclear power is, what is the good thing about nuclear power compared to renewables? High amount of energy, absolutely right. And again, you've got your turbines, long lasting, yeah, 25 years maybe. Constant output, absolutely. As Nicholas Moschetti says, constant output, it gives you a nice solid, something which we really do need today, a base load. So that is really important. And clean energy, yeah, well, let's not dwell on, thanks, Suman. Yeah, let's not dwell on clean energy. There will be some kickback there, but it does have some real opportunities, especially nuclear energy today. There's some really clean alternatives. Obviously, a Fukushima built, you know, in the 50s or 60s in Japan is bad news. And that precipitated a whole catastrophe. That's why the Germans said, look, we've had enough. We're not having any more nuclear power. So it does have, there are issues. So let's just talk about alternative energy sources. Thanks, high energy. Please, everyone, I want to urge you, please look at the chats going on. If you can't see chats, it's really important. Chats. I'll just put a little thing there. Chats. The chats are fantastic. They're very powerful. You will learn a lot from people making comments there. I don't have all the answers. In fact, you out there know far more than I do. So please look at the chats. Most of them are very good. If I find anyone that's not chatting properly, I'll make a comment, but they all look very knowledgeable. I'm learning a lot as well, by the way. So the solar, obviously we've got a whole lot of opportunities here with solar energy and wind energy. Those are the big ones. Ocean energy has been a little bit tricky, like tides, very damaging on equipment, but certainly wind. So solar energy is very simply very powerful. And I've got a few statistics here in a tick, but obviously you have energy from the sun hitting that, and then you get energy there, and your electricity flows to where it's needed, and very small, and away you go. One of the biggest problems when you put solar panels on your roof, I'm not sure if many people are aware, can anyone tell me what the biggest challenge is when I say you're getting a certain amount of energy from your solar panel? Space, yep, definitely space. You take a lot of space, so you need to make sure that the structural engineer does an assessment of your roof if you've got an office building and you've got lots of panels, and please, I beg you, don't make the mistake we made where the guys putting the panels on the roof made nice holes through the roof, which then punctured the roof, which meant when we had rain and water everywhere around the office. Roof orientation is important. Yes, vibration effects. No shading on the panels. No one's mentioning this actually. Impact on the impact on the LV network. That's really important. One of the biggest challenges is the voltages are rising, so we can't get everyone to put in there. Correct direction is really important. No one's mentioned, why would I lose? I'll give you a clue. I don't think anyone's mentioned it. Everyone's putting there. Recycling is a big issue. From the time you put your panel in and you look back a year later, why has the power dropped by 10 or 15 or 20%? Dust. Thank you very much, Bekash. Absolutely right. You need to maintain them. So if you think you're going to get so much power every year, you're in for a bad surprise, because you get dust and rubbish building up on it. You need to go clean it. Please watch out. And faulting wiring, yep, we had a roof here replaced, and the one of the panels wasn't working, and of course the whole structure didn't work. So you've got to make sure your wiring is correct and you're all connected. Okay, I've got to move on. Wind energy, very simple, and obviously mounted at 100 meters or more above the level of the thing. Put auto wiper and spray for cleaning. Yes, you've got to clean. If you don't clean your solar panels, you'll be disappointed. So wind energy, interesting enough, has the velocity cubed is the effect for power. Power is proportional to that. So as the velocity goes up, your power goes up dramatically. So it's a very powerful form of receiving energy. Okay, so now we're going to talk a bit about the transmission of power. So you've got obviously, you're going to transmit it up at a higher voltage. Now, why would you want to run it at 400 kilovolts, for example, in Europe? Affinity laws, yep. Yeah, that's right, Noel, from pumping. Yes, Noel, you're obviously a mechanical engineer to avoid losses. Why would you, yes, there's some very good comments there. Please read the comments, they're very, very powerful. Why would you want to transmit at 400 kilovolts? Why not just transmit at 1,000 volts? Size of conductors reduced. Yes, as we had commented there, basically when you have this voltage, your current is a lot less. So current is low. Once your voltage goes up, your current is very, very low. So that's really important. Ohm's law. Yeah, thanks, Greg. Thank you very much. Absolutely right. So you've got different transmission towers, lightning arrest at the top, cables, insulators, tower, foundation. And you could have wooden poles, tubular steel poles, concrete poles. Why have wooden poles been a problem in Western Australia? And in fact, in some countries, wooden poles. Storm, yeah, storm, fires. Yes, fires can be an issue. And in fact, you think the fire is the problem that burns the pole down. There's also a problem when you've got your transmission lines on the pole. You get, let me just change the color. You get some leakage of current going down into the ground. And what does it do to the pole? It causes a fire. So electric poles then cause a massive bushfire. So, you know, it's not it's not as easy as one thinks. So wooden poles are good, and also you can get leakage of current. And as everyone says, the damage from wear and tear is a lot more with wooden poles. Low current, yep. Achieve this, the supplies at a high voltage. Thanks very much, Dr. Benushi Singh. Yep, absolutely right. Why wooden poles? Yeah, so wooden poles are a problem in Western Australia because not only can they get burnt by a bushfire, but they could also create a fire. If you get leakage from the leakage of current down through from the distribution wires here into the ground, they could cause some fire hazard of the pole itself, and it could be likely to cause a bushfire. Drop there, yeah. So basically, wooden poles are probably not always a good solution. So lightning is another issue, cause huge and produces what they call I squared R losses. That should be I squared R, which basically means I squared R. Can you tell me what I squared R is referring to? Power. Thank you very much, Nagazi. I've got a whole team of gurus here, and obviously tree limbs can cause problems, interference, communication, accumulation of ice. Accumulation of ice can cause problems with conductors in cold countries. What does it do to the conductors? It can pull the whole lot down. So obviously, those are all big issues, losses. Then we've got distribution, and we want to distribute at 230 volts in Australia, or 115 volts, 110 volts in USA. So obviously different voltages, and we will then bring them down. So the voltages I'm going to quote here are probably not always the usual ones. So in Australia, we would have things like 11 kilovolts. You're here, 11,000 volts, 22,000 volts, all the way up to 500,000 volts. In fact, in Australia, you have 500,000 volts. In fact, in Australia, you have 132,000 volts, 220,000, 275,000, 330,000, and 500,000 volts. And in the States, we have a thing called medium voltage, high voltage, and then extra high voltage. And you've got different, well, that should be USA. Can anyone tell me in Australia, when you talk about high voltage and low voltage, what is the gap between the two? 500 volt DC, yep. In fact, you can get 500 kilovolt DC volts as well. Thank you very much, Michael. Yeah, thank you very much. So as Michael says there, up to 1,000 volts, you've got low voltage, and then 1,000 volts, basically over 1,000 volts, you've got high voltage. We used to refer to medium voltage. You don't hear that referred to much anymore in Australia, and they've tended to avoid the medium voltage. They still talk about it, but it's really high voltage and low voltage. So distribution is the next thing. So we get transmission, and then we go down to distribution, and we want to bring the voltages down with what we call substations and pad mount transformers. And believe me, getting a substation put in your area can be a long process. 2 years maybe. So if you're planning to increase your capacity of your building, you may be very disappointed if you go to the local utility and say, hey mate, I need more power. I've got 230 amps at the moment, 3-phase. I want 400 amps. And you may have to wait 2 years, and you may have to pay for a substation. And they may say, you're going to have to find some space on your premises to put the substation. You say, ooh. Or they may say, look, mate, we've got no energy in this area, so it's not going to happen. So what's the purpose of the substation? Can anyone tell me? Why would you have substations? Is it just a waste of time? Set up, step up, you have transforming. Yeah, so basically a substation is a way of distributing current in your area, lower voltage, step up, step down. So you'll always have associated with it transformers. High voltage down to low voltage to feed into your premises in Western Australia, 230 volts. Can you tell me what Western Australia used to have as a voltage? How high did they go in the old days? The very old days when you see Mike Gray. What is the voltage they went up to in Western Australia? Okay, Dr. Benishi Singh has got a comment there. Substation designed to accomplish change voltage from one level to another, regulate voltage to compensate for system. Thank you, Dr. Singh. Precise. In fact, I should hand the microphone over to you. I think you know a lot more than I do. Yes. Okay, so in Western Australia, we actually went up to, we typically run at 230 volts. And 230 volts is a sort of uneasy compromise. A lot of Western Australia was 240 volts. It went up to 250, 260 volts in some of the northern part of Western Australia. And a lot of the European standards is 220 volts. So we've now got a nice compromise of 230 volts. Why is everything just about Australia? I'm sorry, I'm just living in Australia. That's why I'm talking about it. But my slides refer to everything, Abina. Thank you very much. It refers to the whole world. I've got references to everything. So my apologies. I don't want to be sound Australia-centric. So here's the typical distribution industry, the substation. As Dr. Singh says, we will reduce the voltage. And here's a typical example of a little incoming sub-distribution lines. coming in here, lightning arresters, and of course, outgoing distribution lines. So we've got sub-transmission coming in, distribution there, and before them we've got transmission. Is the splitting of, okay, so great place to live. Thanks, Michael. I'm sure your heart is where the, yes, so you're splitting the voltages at substation, single phase or three phase. So good question. You can actually run three phase into your building these days. So in the old days, we only had single phase, but you often see three phase coming into residential buildings now. So at the street level, you'll find the three phase coming in. So good question. So there's a comment there about three phase. When you're looking at your socket in the wall, you'll see single phase, but in fact, often you'll see three phase, which basically refers to a more efficient way of transmitting power. So if you're working in an industrial setting, you'll always have three phase, far easier. So you have you'll have a more efficient way of distributing power if it's three phase, three wires. And then you'll hear terms such as delta and star. Okay, so really there's three components to power flow, and really I'm not going to dwell on this, but effectively you have always a triangle with power flow. You'll always hear terms such as this. S, which is apparent power, Q, which is VARs, which is reactive power associated with capacitors and inductors. And then you have real power, which is associated with resistors, and that's in watts, and this is in VA. So you'll see all three terms refer to VA for apparent power, volts times amps, VARs, which are associated with capacitors and inductances. So you'll see both of those terms. So the question for you is, what's the most common fuel source for power generation worldwide? Yes, so Tony Singh says, can we, yeah, thank you very much, Cole, absolutely. And can I just have a comment from everyone? What are the three color codes for three-phase power? Just give me them, just type them in. Red, white, blue, red, white, red, blue, white. Thank you very much. Red, blue, white, red, blue, white, red, blue, white. Everyone agree with that? Yep, thank you. Okay, that's good. Thank you very much. Okay, so that's the Australian standards. There may be different standards elsewhere. Red, blue, white. Okay, so the most common fuel source and then standard voltages. Thanks very much, guys and ladies. So coal is the most common source, unfortunately 38%. And the voltage for Europe is 400 kilovolts. And you get US also different range of voltages as well. I will clarify all the color codes in a attachment because that is really important. So now I just want to talk about transformers. We spoke briefly about transformers, and really what a transformer does is, here's an example of a transformer. This is a key building block of all the engineering stuff that we do. And here you'll see you've got a coil and you've got voltages, a primary and a secondary. So you can step up, which means the voltage goes up, or you can step down. So this is how you can get 230 volts out, and you can have a higher voltage in. Is it true that if you're colorblind, you cannot be an electrical engineer? That's a very good question. I don't know. I wouldn't think so, but certainly that is a potential problem. So you'll see the different color codes in the different countries. So rather than, yeah, thanks, Michael. Yeah, no, that would be discriminatory if you weren't allowed to. So no. So some statistics for transformers. Efficiency is very, very high, 97 to 99%. So that means you lose very little energy. You can have them for 30 to 50 years. There's two causes of losses, core losses and winding losses, and the size is rated in kilovolt amps and ranges from few kilovolt amps to a few hundred megavolt amps, MVA. So what I'll do is I'm going to give you the color codes in a separate document, so don't go on anymore. Every country has a specific color code. I'm going to give you the important color codes in an attachment to the end of this session, so don't worry, we'll send it out. So two types of transformer losses. Core and winding. Thanks, Scott. Absolutely right. And what's both the transformer and electrical power system? Core and winding, yep, two losses, iron and copper, or core and winding, it doesn't matter. Iron and copper. Thanks very much, Alimon. Okay, and yeah, iron, step up, step down. Absolutely. Thank you very much. Brilliant. Thank you so much. Core losses, and some of you guys answered core losses or iron losses. It's because you've got a core. Here's your transformer. So you've got the copper in the cable, and you've got the core, the iron in the piece of metal, the magnetic material. Thank you very much. And obviously step up, step down. Okay, so next topic is earthing grounding, which is, why would you have two terms here, by the way? Anyone tell me? Why transformers rated in kilovolt amps? Iron core, yep, thanks, safety, absolutely. Earthing, grounding, very important. So you'll see the word earthing used typically in Europe and Australia, Africa, and you'll hear the term grounding used in North America, the IEEE. Total losses, yep, thanks very much. Look, I would love to go into more detail on everything, believe me. So the big thing about earthing is obviously safety. So that's really important. Safety, 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 and obviously lighting protection and protection against electromagnetic pulses, but essentially reduce risk of fires. And the idea is that everything gets taken down to a 0 volts. And obviously two types of electric shocks, direct contact, indirect, very dangerous. Anything to do with electrical engineering, very, very dangerous. And we have a direct contact when you touch the conductors, obviously to be avoided. And obviously indirect is when you're touching something like a tap. And there has been a very bad case recently up the road from me here, where a little girl touched the tap and the electrician hadn't done the right wirings, particularly with the neutral cable, and of course, bingo, the power went through the current went through the tap, and this poor little girl was seriously damaged. So very dangerous. And obviously, the big issue with electric shock is what goes through your heart, and it's in current. So there's quite a few issues there, the path. So very to be avoided, and obviously some horrific injuries, very dangerous. And that's why electrical engineering is such a controlled thing. Now there's two voltages which I want to mention at this section. Thanks, Tony. Obviously step potential and touch potential. Just want to make sure you understand the difference. And the best way to explain it is a little diagram. Here's a touch potential. So here's a structure here, and that's the voltage going down, 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 and that's the voltage going down. And the step potential is the voltage between your 2 feet. So if you're standing 1 foot there, 1 foot there, you have a step potential. And obviously touch potential could be far greater. You're touching that and you're on some surface, and of course you will then have a touch potential. So those are the two. Okay, when you touch the current cable, there's a difference between neutral and earth. Typically in a 2-core and earth cable, the earth wire will be smaller than neutral. Thank you very much, Tim. Absolutely right. These details are all in the slides, so you'll find it's all detailed here. Now there's two types of conductors, bonding conductors and earth electrodes. I'm not going to go into earthing, but basically I've got quite a few slides here to do with earthing because it's a particular area of interest to me. But bonding is when you tie two conductors together, and earthing is when you connect a stake that goes into the ground. Is neutral the same as ground earthing? Can everyone please text and answer in that box? It's not the same thing, no. So basically the idea is that you have a neutral cable and you have a earth cable and you have a earth. So the green, yellow typically here you'll see is earthing, and neutral will be blue, and live is brown. That's in Australia. And we want to obviously connect the neutral down to earth, but they are different. So earth electrodes are very important. It's a whole area of its own. What would be the resistance for an earth conductor to ground? So an electrode is a stake in the ground, and we then tie our earth conductor to that. And again, there's a lot of slides here relating to it. I'll just go through a picture here. Typically, we have lots of different electrodes, vertical rods, and let me just have a quick look here if I've got an earth. So basically what we'll do with an earth is you can have a vertical rod. Typically a vertical rod goes into the ground, and typically we would like a probably maximum of 1 ohm, but preferably 0 ohms to ground. So you can actually, one of the biggest challenges with earth conductors is trying to get the resistance as low as possible. Thanks, 0 ohms. You want it as low as possible because you want to make sure it's, and Pete has made a really, really good point there. Thank you, Pete, for bringing that up. Sandy areas are more difficult to achieve a decent earth compared to wet soil. So it's a whole area of design, really important. Thanks, Pete, really important that. So earthing is very important. Yeah, Australia must be less than 0.5 ohms. You want it as low as possible. Use some bentonite. There are techniques to reduce the resistance to ground. Okay, so obviously it's a really important issue, and I suppose the question for you to answer in this little box, what's the difference in grounding, earthing, and bonding? Electrical systems. So what's the difference? Just type in the box, first one. How do you measure ground earthing? Yep, that's a very good question. There's a whole technique where there's different techniques to measure the resistance, basically using an ohm meter. But there's a whole approach, because one of the biggest challenges measuring earth resistance, which I can tell you from personal experience, is if you've got any stray electric currents in the area, you could have a problem. So Dr. Benushi Singh has got a really comprehensive answer. Bonding is a connection of non-carrying conductive elements like enclosures and structures. Grounding is the attachment, or earthing is the attachment of bonded systems to the earth. Both are necessary to safeguard people and property from. Thank you so much, Dr. Singh. Very comprehensive answer. And what's the maximum allowed resistance for an electrical ground under Australian and under the USA code? Anyone? I'm sure the Australians won't care about the US, but it'd be interesting just to know. Yeah, so as far as I know, the Australian maximum resistance where you can't go above is 1 ohm. As far as I know, it's 1 ohm. So the NZS 2018 is 1 ohm, I believe. And in the States, 25 ohms under the NEC code. So it's high. Obviously, 1 ohm is not a good one. You want it 0.1 or 0.01, but that just gives you an example of the resistance, just to give you. Why would the US be 25 times higher? So Scott, a very good question. That number is the maximum, and they actually define, the NEC code actually defines each individual area with specific numbers, which I haven't quoted here. So it's actually a lot more complex. And as Pete said, everything's bigger in the USA. Pete. Okay, so power quality is the second last item. I've got to run, unfortunately. I know people are getting irritated. I can't carry on forever. So I just want to go through two more items, power quality and power system protection. So power quality is trying to say we want to try and keep the quality of power as clean as possible. So you get fluctuations, dips and interruptions, power frequency variations, and harmonics. So there's different variations here. I just want to look at a few of them. I'm not going to look at them. You hear things such as voltage sags. So it's a decrease in the voltage due to local and remote faults. And you could have, the result could be that your computer crashes, bulbs glow dim, fan speed reduces. The voltage swells. Thanks, Dr. Singh. Very good point there. Single line to ground faults would cause this problem here. Equipment misoperates. So basically with these issues with power quality, you can have some unhappy issues with your equipment. Over voltage, load switching off and on. Capacitor switching on is another one. You may say, why would anyone worry about capacitors on your power system? Can anyone tell me? I had a particularly bad event with capacitor. Yeah, voltage spikes. Why would you have capacitors on your system? Yeah, thank you. Absolutely. Who was that? Varun. Yeah, thank you. Power factor correction. Thank you very much. Yep. And in fact, I had a particular bad event. I won't mention the installation, but we had these guys doing some testing with capacitor banks, some consultants. I won't mention their names. Anyway, they connected all the capacitors onto the end of the transmission line or the distribution line. Let me get it right. And I was testing my variable speed drives. I had 15 variable speed drives in my MCC, motor control center. I walk in and I see, to my horror, every one of them, over voltage, over voltage, over voltage. They'd all had a spike going through them due to these guys putting the capacitor bank on, fully charged. So I had the spike going through my whole plant. And I was just installing. I had to then, it was an absolute disaster. And of course, we fortunately could pin down. I was measuring the voltages at the time, so I could pin down exactly when the spike came through, and I could pinpoint who did it. It was a very awkward situation because it was a colleague of mine from these consultants. Anyway, undervoltage is another problem. Brownouts, as you sometimes hear referred to, mixers and grinders may not start. Variation of frequency from the fundamental frequency, that's another potential issue. Equipment failure would result. So these are all issues that you need to watch out for. Solar impacts, yes, that could be an issue as well. Surges, so this is an increase of 110% of the normal voltage. Surge protector can help you, so that's particularly important. So some countries where you have a lot of spikes, you need surge protectors as a critical part of your life. One issue here is you're dealing with data communication systems. What's the best form of protection? Can anyone tell me? DC block, yeah, surge arresters are helpful. Best thing is to go for fiber optics. Beautiful, no connection to the, for your data communication systems. What's the doing, team? Batteries, how to improve power quality. Yep. So these are all issues with switching. And obviously lightning can be a problem, and there's different types of flashes, high voltage transient, and obviously potentially big problems. So you need to make sure you put surge arresters in, otherwise you will pay a price. And as I said, try and use fiber for any communication system, so make sure your computer is protected. And also sometimes you find your computer locks up, your equipment locks up. It may be a spike coming through your data communication system. Fiber will solve that. So obviously to be avoided at all costs. So lightning is surge arresters. And obviously what I want to show you is that if you put your oscilloscope on, what a poor power quality will show you is something looking like this. So that's the sort of signal. So you should see a nice clean sinusoidal signal, but you see that. Yeah, you get all the slides, don't worry. Galvanic isolation can help, but fiber optical isolation is the best. So you want a clean signal and you get that. And basically this thing, you can actually use what you call a Fourier decomposition, and you'll see that a signal like that is decomposed into a whole series of harmonics, different frequencies. So when you hear harmonics, it's basically a badly distorted signal voltage, which is broken into a whole lot of different harmonics, different frequencies. Not all comms have fiber interface. Yep, that's true. Absolutely right. So lots of issues with power quality, and obviously the point to make is that billions of dollars. Most common is voltage sags and swells, 80% of all power quality events. And the other point is power quality monitoring can help. So you can use Adranets to monitor and diagnose. So I suppose the first question for you there is, okay, question is, will there not be clean power from the generating station? Absolutely right, Locke. The generators, suppliers have to have clean power, but unfortunately, with all the electrical disturbances, lightning, people switching on and off their power, it all creates lots of rubbish, electrical rubbish on your lines. So that's the problem. Okay, so question is, what is the result of the power quality issue associated with the presence of harmonics in an electrical system? Can anyone tell me? Yep. Okay. So high electricity costs, noticeable decrease in equipment reliability, power surge. Yeah. Thanks, Michael. That's what I was looking for. But all the other comments are quite right as well. Extra heating. Thank you very much. And what's the purpose of power factor correction in electrical systems? VAR compensation. Yep. Absolutely right. So basically, the idea with power factor correction is really putting capacitors in means that if you plot your voltage, that's your voltage, and this is your current, we try and keep them as close as possible. So we want them basically as close as possible to each other. So power factor correction always helps because most of our loads are inductive. So putting power factor correction in, we can actually line them up. Thanks very much. Yeah, the suggestions from everyone are just perfect. Thank you. So increase heating, reduce efficiency. So I think everyone got that. And power factor correction is to reduce the amount of reactive power. So reactive power is associated with inductors, and we put capacitors in, and that cancels out the effect of the inductors. So inductors, you have lagging power factor. Capacitors, you have leading power factor, and you bring them together so your current and your voltage waveforms just line up. Yeah, you can get all the slides, no worries, don't worry, all will be well. Okay, so the last section I want to do, and Barry, I'm so apologetic, I've overshot by 15 minutes, so I'm probably going to be shot at dawn. I just want to finish off with the last component here. Barry, are you still with me? Or have you
It's okay.
fallen asleep?
It's
Is that
okay,
okay?
Steve. I'm still here. Yeah.
You're still there. Thank you very much, Barry.
Yeah.
I'm sorry to overshoot.
All good.
Another 7-8 minutes. I just want to cover the last topic, which is protection. And protection is so absolutely critical. And it's a topic very close to my heart. So I just want to mention it so you know what protection. So you've got two types of faults: incipient faults, which is a breakdown in insulation. And some of you may remember, if you've got gray hair like me, insulation, which was sort of paper insulation around cables. And of course, old cable PVC is worn down, and of course, you get slow leakage of current. And solid fault is a fault from something damaged, complete breakdown of insulation, solid fault. So really, transient faults are, tree branch falls across your power cables, it will all be sorted out, just temporary. Permanent fault is something where you've got a permanent fault, and as soon as you try and reclose with power, it'll trip out again. So we've got two types of fault: transient and permanent fault. So just want to spend a few moments. What about a 6 ohm snake? Thanks very much, Michael. Thanks, Garth, for coming along. I'm sorry I was overshot on time. Protection is needed, obviously, to avoid electrical shocks, electrical burns, and obviously every household has protection, earth leakage protection, which I'm not going to be spending time on here. And we obviously need to look at overload, overvoltage. Overload protection, protect from hazards, and overvoltage. So overcurrent, where the current goes up and it goes beyond the rating, and we need to protect the cables and the equipment. So we can damage, and overvoltage can also be damaging. So the best, easiest device is, thanks so much, Pete. I'm sorry, thanks, Garth, for coming along. Pete, thanks. Fuses are obviously a very important protection. But the problem is, once you blow your fuse, that's it. You have to replace the fuse. Although there are some very clever strategies in place today. So fuses are obviously types of non-varying loads or widely varying loads. So if you have a what we call a DOL, direct online motor, when you start the motor up full power, and yep, is it GF4, Mr. Augustine? I'm coming to relays in a tick. So fault detectors, interrupter, we need quick action. We don't want any wastage. And as I've had suggested by my team here, circuit breakers are the other one. And obviously these are probably the ones you see all the time. And basically electrical switch, but automatically operated. And it can be reset. Obviously, you don't want to reset it when you've got a permanent fault. Obviously, you don't want to reset it when you've got a permanent fault. And fuses, protective relays, and circuit breakers are used. So here's an example of relay circuit breaker connection. And obviously, one of the big points is a tripping battery, and effectively this will protect your main circuit. So the idea is that this contact is broken here, and you then interrupt the current flow when you see a certain. Thank you so much, Michael Brazil. I'm sorry to overshoot on the time. Purposes of circuit breakers, obviously switching loads, break the fault current, and carry through the fault current safely. And obviously, as I said, speed is really important. And I'm just going to quickly show you the diagram for speed, why there's a problem here. Can you see here, this diagram here? The fault occurs here. There's a pickup of the relay there. So the relay picks up there, and the trip coil's energized at this point, and there's obviously a bit of arcing going on as the contacts are separated, and then the fault is extinguished, and then the relay is reset. So bear in mind that even when your contacts are opening, you get some arcing going on between the contacts. Obviously, your total fault clearance is from here, from the time to the time the fault is cleared. So it can actually be quite long, even though it's in milliseconds or shorter. So relays are electrical switch, and I'm not going to worry about that. I don't have the time. Ultimate goal is to disconnect a faulty system as quickly as possible. So these are really important, and the design. So power system protection can result in outages costing billions of dollars every year. This is obviously the American, and protective relays are key. And obviously one of the biggest challenge here are with power system protection. I just want to highlight to you now is that solar and wind are also giving us some challenges there as well. The arcing is known as switching debalancing. Yep, thanks very much, Mr. Dr. Singh. So first question is, what's the most common type of protection device used in electrical power systems? And what is the purpose of a differential relay in electrical power systems? Over to you. Well, the relay reset, yep, the relay keeps tripping. Fuse, CB, yep, circuit breaker, yep, thanks very much, absolutely. So obviously a circuit breaker, and obviously the idea is to detect current imbalances between two or more phases. So what we mentioned earlier on, I didn't speak about it in length, but with a three-phase system, you've got three phases coming in, and you've got a imbalance between them. Okay, so in essence, I want to thank you very, very much for coming along. I've just gone through everything in a very, very fast rate of time in an hour. I apologize, I'm not, but please, I will summarize a few things in a return in my messages. One is the color of the phases, because that is really important. And also there were a few questions here which came up, which I'll also answer. Unfortunately, I couldn't answer everything now, but I'm so grateful for you all listening to me for so long. Very appreciated. Thank you so much. Really appreciate it. And I want to hand the microphone over to my good colleague, who's hopefully still...
I'm still here, Steve.
Yeah, excellent. And
Okay.
he will take over from here. And thank you so much, one and all. There are more slides than you can poke a stick at here, but you will get all the slides and all the recording. And I've got some additional information, as I said, with the colors of the phases that is really important. I want to just highlight that. I do not want you to kill yourselves. So thank you so much for attending. And over to you, Barry, Mr. Dokotla.
Thanks, Steve. Just want to say big shout out to everyone, all your participations and your reactions on the chats. And yeah, please feel free if you have any feedback, any suggestions. We really want to hear from you. So I'm just gonna move on to, if you can just see on this next slide here, it's just our upcoming programs. So you can also just go on our website to view our course schedule. That will give you the whole details about our upcoming programs. The next one should be our upcoming webinar, which will be on the 24th of May. And then we've got the next one, which is coming the 1st of June. So if you are interested, you can just go on our website in order to sign up. And just to touch based on previous slides when we were talking about the certificate of attendance. So you can actually take out your phone and scan the QR code in order to complete the form. If you're unable to scan the QR code, I'll just share the link on the chat, so you can just follow that link to complete the form. Please note the certificate of attendance will be shared to you in the next 1 to 2 working days. Okay. Don't know if we had any last question. Anyone who's got any last question?
There were 3 billion questions in the
Yeah.
In the chat. I've tried to answer most of them, but some of them I will go through and answer because they do require a more comprehensive answer than I could. Some of my answers are a little bit simplistic, but I will answer
Yeah.
them in more detail.
And
I'll go through the chat. If I can get the chat recording, I'll go through that and put out some. There were some really important comments that some people were very generous with their knowledge, like Dr. Singh. I need to just repeat that in the materials before we send them out, Barry, if that's
yeah.
okay.
Thanks, Steve. I'll just share
Thank you
our
both.
email address here, so feel free to reach out if you've got any suggestions. If you have any feedback, you can send us an email. Otherwise, thanks everyone. Thanks, Steve.
Thank you very much, Mr. Barry de Kotler, and thank you so much, everyone in the group. You are just so incredible. I'm so grateful. I've learned more from you than you ever have learned from me. I will respond with some more detail, but thank you so much. Really appreciate it. I'm now going to go and munch an apple and drink some water. Thanks so
Great.
much, everyone. Cheers.
Cheers.
Thank you very much, Barry. Stay warm
Bye.
and dry in
Thanks, Steve.
Johannesburg. Thanks so much, Barry. Thank
Cheers.
you.
Bye.
Bye, bye, bye.